that record, and I think I'll cut out my stop video. There we go. Let's see. I thought we would. I do a little more with the software. We never did build that rate file, and then that's a little bit complicated if you don't have experience at it. So this is the assignment. So it's the GSA 3 rate that we're wanting to put in, and then these are the gas rates. I think we said what, outside Cookeville. So large, small, commercial, we'd probably be down here in these type of rates. So we'll get to the gas rates here in just a second. Let's see. So let's pull up the rate structure. And so this is the GSA 3 rate that I emailed out to you. And so, you know, we start going through here. And let's say, so this is for service that's 1,000 kW or more. And I'm not sure, that building may actually be too small for this, but we said do the GSA 3. So we're going to do this rate, whether it really applies or not. So your basic service charge is $934.50. And then we have this TVA grid access charge, which can be, you know, either $205.30 or $579.04. And it depends on how big the utility bill is. Well, you know, so how are you going to figure that out? Well, what you can do is you have a model of the thing, and it will, as sent to you, it will run. So I would suggest to figure that out that we just, you know, pull up the model, and it may not be perfectly configured right now. I guess we probably should look at it. Let's make sure we at least have the right chiller in here. Let's see. Yeah, we do have the centrifugal chiller and the hot water boiler. So that's good. So that's pretty close to the base case configuration, I believe. So if we just right click on this, then we can see the simulation results. And if you're doing this to check the energy, you want to make sure that this billing details report is checked, and it says electric, or the electricity consumption. And then if you do preview, it'll run real quick. And the billing details at the very end. I know that by experience. You would probably have to look at it. And we do see our KW doesn't meet the 1,000. So I probably should have done this on GSA 2, but we're not going to change the assignment at this point. I didn't really think about that. But here you can see the consumption totals that we're getting. So for the year, we're pushing 1.9 million kilowatt hours. And so that's, we go back to the rates here, and we see that if the customer's average monthly kWh usage during the last 12-month period is greater than 150,000 kilowatt hours, then it's this number. So to get our flat charge, we have to add those together. And so I'm going to get out my calculator here, 934.5 plus 579.04. Okay, so that's 1513.54, just adding these two numbers together. And that's going to be a monthly, you know, flat fee. Okay. So let's go back to the program, and let's go to electric rates. And let's just, I've got a GSA rate from before, but let's just start this from scratch. And we'll call this GSA 3, and we'll say it's NES, and it's 2021. Okay. And this is definitely a complex rate, so we're going to have to check that. And then let's see, I've done this. So demand units, KW, flat price, no, that's grayed out. That's if you have a real simple rate structure. So customer charge, that's going to be that flat rate, these two fees. So that's 1513.54. And the tax rate, I think I said use 1.5%. You know, this is a commercial bill. 1.5% is a manufacturing tax rate. I believe for this one, we probably should use 5%. Come to think about it. I mean, I'm not going to be a real stickler, but you need to put some sort of a tax rate. And that's something we could check. Gosh, I don't work in that many commercial buildings, so I'm used to looking at the manufacturing tax rates, which for Tennessee is supposed to be 1.5%. Okay, let's see. And I believe we do have seasonal scheduling, so we can check this. And so January is going to be winter, and February is going to be winter, and March, I believe, is winter. We can check that on the rate structure. And we have April and May are like transition or mid, and then we've got June, July, August, and September, and then we've got 2 more mids. There we go. So we've got, whoops, and that's got to be winter. Okay. So it's going to take a little while to put this rate in. Let's see. Do we have time of day scheduling on this? I'm not sure. We'll check the rate and then we can come back and add that. Well, here, I printed it out. I've got it in front of me. So this rate, now this rate doesn't have time of day. So we don't have on peak, off peak in this one. Okay, so that's a little bit of a simplification. Okay, so let's go, let's see. The first one listed is the demand charge. So let's go to the demand charge. And so let's say, this is going to be for, let's see, I guess we have to check here. And we'll put in, the first one listed is summer. So we'll put in the summer. And then for all periods, let's see. Oh yeah, that's all periods of the day. So that's, we can leave that at all periods. And the rate says for the first 1,000 kW, so this block size, the first 1,000 we pay for here, and the value is $19.80. Wow, pretty pricey. 19.80. Okay, and then we're going to check the next box, and this is still going to be summer and all periods of the day. And let's see, this is, I think, all of the, let's see, yeah, excess over. Okay, so this is all of the rest of them. So if it's all of the rest, you leave the nines, the 9999999. That's kind of what the program means by that. And so this rate is $19.93. So we go 19.93, and we've got that one. So we've got the demand charges for the summer, and then we're going to go here. And let's see, the next one listed is winter. So we'll go winter and all periods. And again, it's going to be 1,000. Once you get the hang of this, it goes pretty quick. This is 1884. 18.84. And then we click again, and we go winter again, and we leave this, and then we put the final rate, which is 1897. I don't really change all that much. And then we got to get the mid, or the transition months. So we'll go mid-season, and this will be 1,000. And it's 1884. It's the same as the winter. 84. And we click again and again and again. And it's probably 1897. There we go. Okay. So that's good on the demand charges. And now we have the energy charges. Let's see. And so we have, oh, we do have on peak and off peak. Okay. We don't have on-peak and off-peak for demand, but we do have on-peak and off-peak for energy. Yeah, summer period, all on-peak plus for all off-peak. Okay, so we do have, okay, so let's go back to the general tab. So we do have time of day scheduling. And so we'll have to do a schedule, create new schedule. So time of day schedule, utility rates, hourly profiles. Okay, so I'm pretty sure, let's see, determine on-peak and off-peak hours. The only on-peak, you don't have on-peak on Saturdays, Sundays, and holidays. Okay, so we'll have to remember that on the assignments. And then let's see, so we're 1 p.m. to 7 p.m. during April, May, June, July, August, September, and October, and 4 a.m. to 10 a.m. during the months of January, February, March, November, and December. Okay, so let's go ahead and do this. So let's get this one. And so we're going to call this, this will be, say, summer on peak. Summer on peak. Okay. Okay. And so, let's see. So the summer, it's 1 to 7 is on peak. That's 1 p.m. So that's what, 1300. So I've got 0 to 12. And if you hit, come over here and hit probably O for off peak. And then we've got 1, 2, 3, 4, 5, 6, 7. So 7, what's that, 1900? So this would be 20 through 23. And this is also off peak. So 1, 2, 3, 4, 5, 6, 7. Is that right? From 1 p.m. So that would be from 1 to 2, 3, 4, 5, 6, 7. I've got one too many. So I think there's 13 needs to go off. There we go. So that's 6 hours. 1, 2, 3, 4, 5, 6. Okay. So that's pretty good. And now we'll do the winter. Winter on. Winter on peak. And this is from 4 a.m. So 4, 5, 6, 7, 8, 9, 10. Yeah. So I guess I'll start this 0 to 5. It's going to be off. And I need this to be 10. So this would be 11 through 23. That should be off. Okay. Is that 1, 2, 3, 4, 5? No, that's not enough to 9 p.m. So I guess I need to put this at 5. So that would be 1, 2, 3, 4, 5, 6. Okay, so that's pretty good. Okay, so let's go to assignments. Okay, so Saturdays, Sundays, and holidays, you can hold your mouse button down and you can get all, just shade them all, grab them all. And then, so we'll make that a 3. Let's see. Oh yeah, so we've got to do another one because we don't have any on peak hours. Okay, so I'm going to do this one. I got to go back over to here. Okay, so this is going to be 0 through 23, and these are all off peak. There we go. Okay, so Saturday, Sunday holidays are all, there's no on peak hours. And then, let's see, for design, I'm going to put 1 for design because that's the summer. Doesn't really matter. Well, it doesn't really matter for, this is just billing rates, and the design is only for equipment sizing, so it doesn't really matter, I think, what you put there as far as the cost is concerned. And then let's see, so we have our summer months. Yeah, 1 to 7. April through October. Okay, so January, February, March, April. Friday through October. Those should all be 1s. And then I guess we can go ahead and set these as 2, 2, just to be consistent. I don't think it matters, but there we go. Okay, so for Monday, this is January, February, and March. So we get to winter, and then we go to the summer, and we go back to the winter. Let me make sure that during the January, February, and March, and then November, December. Okay. So that's okay. Okay, so we have our scheduling there. Okay, and so now we need to do the energy charges. Let's see. So let's do, you check the box, energy, and so this will be for summer. And this, the first one is for on peak. And so this will be peak. And there's only one rate, so it's all of them. So that's good. So this is 6.688 cents. So then this is dollars, so 0.0668. Okay, and then we'll come in and we'll check the next box. Again, this is summer, and this will be for off peak. And so then this is 5.632 cents. So 0.05632. Okay. And we're getting the hang of this. So we'll go to winter. Well, it says mid-season next here. So do mid-season. Oh, there is, no, we don't have mid-season. That's right. It's either summer or winter. So actually, we do have mid-season. Let's do winter. I need to think about that for a minute. On peak. That's all of them. And so for the yeah, we do have a transition period here. Okay. So for the winter though, 0.06267. And then for the winter again, this is the off peak. And this is 0.05663. And this is the mid-season. And this is going to be the peak. And for the transition period, oh, I say for the trend, it's all the same. They don't have on peak, off peak for this. So we can just put all periods for this one. And this is 0.05783. Okay. I think that's got it. Now let's pull it back up and just take a look at it. So complex rate, we do have seasonal scheduling. So these are our seasons: summer, 4 months; transition, spring and fall, 4 months; and winter, 4 months. Demand units are KW. Customer charge, that was the grid access plus the base customer charge. And right now I stuck 5% tax on here, something like that's fine. Okay, and so for the energy, we've got on peak and off peak. For summer, winter, and in the transition months or mid-season, it's all the same. There is no on peak, off peak. And then demand, we've got the first 1,000 and then the rest for summer, winter, and mid-season. And I think that's about it. So that looks pretty good. Okay, let's get the gas rate in. And we'll do, well, actually, I think I've already done this one. This one's pretty simple. I think we'll just look at it. Let's see, I printed this someplace. Okay, so I have the numbers in front of me. We may want to change the numbers. I think I said use Cookeville outside. So let's see. I've got 7.5% tax on this one. Yeah, that's probably better. I think we'll change the other one to 7.5. But again, on what you run, I don't really care all that much. Fuel charges. Let's see if these are the same numbers. Let's see. Okay, so let's look at general over here. I went through that pretty quick. So this is not seasonal, and this is fairly simple. We don't have time of day or seasonal scheduling. We just basically have one, and it's just different block sizes. We do need to look at units. Okay, and this is dollars per therm. Okay, is the unit. Okay, so you may not be familiar with therms. A therm is 100,000 BTUs of energy. Okay, when you look on the bill, it says CCF. And so the first C stands for 100, the Roman numeral, and then the CF is cubic feet. So 1 cubic foot of gas is, nominally speaking, 1,000 BTUs. So 100 cubic feet is 100,000 BTUs. So these units are essentially the same. Now, a therm is defined to be 100,000 BTUs, and the energy content of the gas can change, from one location to the next. And sometimes on a bill, you get a factor, a BTU factor that tells you for that month, how close your gas was to 1,000 BTUs per cubic foot. But it's usually pretty close. So for this purpose, that's fine to assume that a therm and a CCF are the same thing. So our units are okay. We could change this to CCF if we wanted to, and it would appear that way. So we see for this, you check this first box, and so it's the same for all seasons and all periods, and the block size is 100 therms or CCF, and this is the cost. It's 92.4 cents per therm. The next 200, which would be block 2, it's 0.899. That's correct. All right. And then we get the 999, which means all the rest are 0.874. So that's just pretty simple. No issues with that at all. So we'll say, okay, I'm going to go back and change that tax rate just so they're consistent. This is the one. I guess that's right, 7.5 for commercial. Can't remember everything. Okay, so now we've got our rates in there. So now when you go back to the building, you got to make sure that you have the correct rates associated. And so you go down here to the meters and see this is on inside. So I'm going to set it on outside and then put it on the new GSA rate. That should be good. Average building power factor. This is stuff that we really don't have to put in. Source generating efficiency, that you can get reports that take it back to the source energy, like the coal or the natural gas or the uranium energy that had to be put in at the power plant in order to generate the electricity in order to, satisfy the needs of the building. You can get reports on stuff like that. Okay, so let's see, we got plants. We're doing the centrifugal chiller. We're doing the hot water system for the heating. We got all of our air handlers in there. We don't have any miscellaneous energy, and we got our meters right. So that's okay. So we're ready to simulate. So you right click like before, view simulation results. We got just about everything checked we can check, and you hit the button. Of course, this will change the numbers from, whatever, because we got different rates. Okay, so let's look at this a second and take a look and see what you're being told here. Okay, so first, I guess the first 1, 2, 3, 4, 5 categories are all what this thing considers the HVAC subtotal. So we've got air system fans. So in that fan definition, we gave it, I think we gave it 1.2 inches of static pressure. It calculates a flow rate. It's got a fan efficiency. So it calculates the amount of energy that it took to run the fans for the entire year. And then cooling, that would be to run the chiller. And then for the heating, that would be boiler fuel. And then pumps to circulate, we've got condenser water pumps feeding the cooling tower from the chiller, and we got chill water circulation pumps. So we've got 2 sets of pumps at least, and I think there's a small pump on the hot water loop as well. So we got 3 different sets of pumps running here. And the heat rejection fans, that's the cooling tower. So if you don't have an air-cooled chiller, you have to have a cooling tower. If you have a chiller, and then you have to have fans on the cooling tower, and that's what the heat rejection fans are. They're on the cooling tower. And then we get lights, and we get equipment. That was some of our interior loads. We didn't put any other miscellaneous loads in. So we see the HVAC subtotal is about 113,249, and lights and equipment are 150, almost 152,000, and so our grand total is 265. I am recording this, aren't I? Yeah. Sometimes I forget if I'm recording or not. And then you can get it per square foot, and oh my goodness, it just goes on and on. Annual energy emissions, that's the energy, the dollars of electricity and natural gas for HVAC, non-HVAC, and there's lots of different reports. If you go down here, some of the pie charts are nice. They're pretty. And again, you can save this. Here, I'll just go ahead and do it. Let me do this. Simulation report. Let's see. We'll put this in the homework folder. homework. There we go, 2021. And so this billing simulation report, I'll call it base case. HAP1, because we're going to have more than one assignment using this software. Okay, so I save that. And now if I go in the folder, it's a file that I can open with Word. Okay, so I encourage you to look down through here. You go down here far enough, you start getting, this is kind of interesting. So you see monthly component cost. And so, you know, it starts home. That's my puppy dog has just come upstairs with me here and she wants to play. So I can't do that. So you're probably going to hear some barking in the background. So we start over here with the fans. You can see this would be the fans. And then we have cooling. Well, we're not doing cooling in January, maybe not much in February, March. And then you see the cooling energy come up, which you would expect. And then we see we've got heating energy, which is pretty big up through here. And then it comes back up and the pumps and all that stuff. I have an extra diversion now. And you can see the dollars per se, and these are cost plotted here. So this is the numbers that go into that. HVAC electric, gas, and non-HVAC electric. You see that plotted. And then you can get on here to more detailed stuff, kilowatt hours, therms of gas, all that sort of thing broken down on a monthly basis. So you really get a lot of good information out of this. We get into the cost, and then we get into, this is the electric bill down here at the end. You can also request the gas bill. Okay, so enough of that. I'm gonna show you one other thing here. So this was my spreadsheet that I put together a number of years ago. I think this is from 2017. And so there's some of the stuff that you've been asked to simulate. This was a slightly different assignment, but I just thought you might see this is, I think, a pretty good way, and it doesn't have to be this format, but this is a pretty nice format. So I came here and I list all of the different categories that I want to track. And then base case, so that's my fundamental, you know, my starting point. And then it's like airside economizer. You know, if I was thinking about investing some extra money in order to have an airside economizer, what would my, you know, what would it do to the operating cost of the building? And so you can see, you know, it affects the fan energy, affects all this sort of thing. And so this is total operating cost. And you see total savings on this simulation, I got about $9,900. And so then the question is, well, how much do I have to pay to get all of this whiz bang put on all my air handlers? Is it a good investment? And then this would be dry bulb temperature control. And we see the enthalpy, well, it gets us a little more. We're 10,000, about almost 10,700. VFD on cooling tower, different chillers, setback, all that sort of thing. And then, so there was some other stuff. This was NES time of day rates. This is Washington, D.C. rates, just running some different rates around. And then make this smaller so you can see I did a bar chart, and this was with NES. And so it shows for all of the different simulations, total HVAC cost, you know, water cooled centrifugal, one stage absorption, two stage absorption, all that. So you kind of get a feel for, you know, the impact. So anyway, some sort of a presentation like this is what I'm looking for. Something nice, neat, concise that conveys the information that you can look at pretty quickly. Okay, enough of that. All right, so we're now going to move into the next kind of block on the course here. And my puppy dog, his name is Nellie, and Nellie's pretty excited about this chiller. She wants me to throw toys so she can go fetch them. Okay, so we have looked at centrifugal chillers a little bit, and I do have a video, a short, I think it's a 4-minute or something. There's some YouTube videos, a little more detail on centrifugal chillers that I think I'll send out to you with this link that I want you to watch. But this is a different technology that can produce chilled water. And it gets mentioned perhaps in thermo, but I think it probably gets glossed over pretty quick because there's just not time to do all of this in thermo. So this is the absorption cycle. And so this is a little bit of a I would say kind of a chemically based cycle. But energy-wise, the big difference is the main energy input is thermal, is heat. And the efficiency is not great, but where you see these things that really shine is where you can operate the chiller with waste heat that you were throwing away. And so sometimes plants have significant streams of waste heat that go directly to atmosphere, and sometimes they can recover that heat. If you can get 220 degrees into, say, water or a steam, or probably water, hot water, something like that, you can drive this absorption cycle. And, so the electrical loads are very small compared to, a big centrifugal chiller. I mean, you may have 1,000-ton centrifugal chiller that has, I don't know, a 500-600 horsepower motor on it. And if you did 1,000-ton absorption chiller, you might have a 20 or 30 horsepower, and the rest of the energy input is thermal. And if it's free thermal, then that's really a good thing. So anyway, one of the goals of this course is to go into some depth and detail on the absorption cycle to let you know that it's out there. Okay, so absorption system fluids. So what we really have here is, we'll see as a refrigerant pair. So there's two common ones. Probably the most common for HVAC is water and lithium bromide. And we'll see the lithium bromide on the next slide, where water is actually the refrigerant. You probably never thought about water being a refrigerant, being able to be a refrigerant, but it is, and it's utilized in the absorption cycle. Water is really good for heat transfer. High latent heat of vaporization, nominally speaking, 1,000 BTUs a pound, which is a bunch of energy for a pound of fluid. Like if you boil it off, or when you do the phase change, latent heat of vaporization, either you condense it, you pull out 1,000, or if you boil it away, you got to put in 1,000. It's stable, non-toxic, low cost. Just to give you a feel for this, inside the evaporator, if water is the refrigerant, water boils at 40 degrees Fahrenheit if the pressure is 0.122 psi. So atmospheric pressure at sea level is 14.7. So that's roughly 1/100th of an atmosphere. So it's pretty low pressure inside this absorption cycle, especially in the low pressure side, the evaporator. Okay, so the absorbent with water as a refrigerant is lithium bromide. And its characteristics are, it has a high affinity for the refrigerant, the water. They like to kind of team up together, go into solution. The lithium bromide has a high boiling point, so if you start heating that solution, you can vaporize the water pretty easily, and the lithium bromide stays behind. It's a non-toxic salt, so we do have corrosion issues that have to be dealt with, and it's also low cost. So water is low cost, lithium bromide is low cost, so it's a pretty cheap refrigerant. The other pair that gets used more in industrial for really lower temp freezers is ammonia being the refrigerant and water being the absorbent. So ammonia water is a pair. They talk about refrigerant pairs, and water lithium bromide is also a pair. In the water lithium bromide, the water is the refrigerant, and in the ammonia water, the ammonia is the refrigerant. Interesting. Okay, so main differences between these slides called mechanical or the vapor compression and the absorption cycle. In the vapor compression mechanical, we have a compressor. And in the absorption cycle, we lose the compressor and we pick up an absorber, pumps, and a generator or concentrator. It's called by different terms. So the common component to both cycles are the evaporator and the condenser. And there is some device that causes a pressure drop because we have to drop pressure from a high side to a low side if we're working with a refrigerant. So that got left off. Okay. So on the absorption cycle, the generator and condenser operate at on the high pressure side, which is not very high. It's about 70 millimeters of mercury, which is about 135 psi-A. And so what is that? That's roughly 1/10 of an atmosphere. And then, which is again, that's a vacuum. The high pressure side is a vacuum. The low pressure side is a pretty hard vacuum. So it's about 10 times lower than the high pressure side. So the evaporator and the absorber operate at the low pressure, which is about 0.12 psi-A. Okay, so through this end, this just reminds you what the mechanical basic components, we've seen this before, but you got a compressor, superheated vapor at 2, you got to condense it at high pressure, and then it goes through the expansion valve. We get some flashing. The majority of the refrigerant is still liquid coming out of the expansion valve at low pressure, but it's cold. And then it goes into the evaporator where it evaporates and it takes heat out of whatever fluid stream is passing across the evaporator. Refrigerant gets boiled away at 1, goes back into the compressor, and we repeat. Okay, so this is the overall schematic of a single stage absorption. And so you can see all of the different components. Let's see. Can I turn on? Yeah, let me turn on my arrow here. There we go. So this is where the hot water or steam is introduced into the chiller that basically drives the cycle. Okay. Over here, we've got cooling tower water that's coming in. It goes into the absorber, and then it goes into the condenser. So we actually are going to be dumping more heat. So we're going to need, for a given size chiller, we're going to need a larger cooling tower with this absorption cycle than we would with a standard centrifugal vapor compression chiller. And so we're going to go through each one of these systems on independent slides. So let's move on here. So he's showing supply and steam at 244, and then we have condensate at 237. So that's the thermal input over here. You can put hot water in this, and I've seen them operate down at about 200 degrees on the hot water temperature. I mean, I think the COP goes down and they don't operate as well, but I think at least some of the units can be operated down there. So let's see what it says here. Refrigerant vapor liberated in the generator is induced into the cooler condenser. Prior to entering the condenser, the vapor passes through an eliminator grid. I guess for some filtration or additional pressure drop. I guess a number of reasons for the grid. But basically, so what's happening is we are pumping a solution up here that has the lithium bromide and water. It has a high concentration of water, or it's called weak solution. It's weak, meaning that the concentration of lithium bromide is weak because it has a lot of water. It has maximum water content, we'll see. And so then when we put the heat to it, the water boils off. And so we get water vapor coming over here to the condenser side. And when that water vapor hits the outside of these condenser tubes that has cooling tower water flowing through it, like roughly 100 degrees Fahrenheit, something like that, it condenses into the liquid stage. And then it kind of pools up over a little bit down at the bottom of the condenser. So this is what we go, well, let's see, I think we've got individual slides. Well, there's a bunch of the slides here. But anyway, this is called the generator, and it's because we put the heat to it, and we generate the refrigerant vapor that then moves over to the condenser. Okay, let's see. Water returning to the tower is heated to about 103. So this is talking about our cooling tower water, which comes in from the tower at 85, and it goes through the absorber where it picks up some energy, because this is where the evaporated, this is on the low pressure side of the system, and the evaporated refrigerant, the water vapor, recombines with the lithium bromide, and that reaction is exothermic, and so it's given off some heat, and that heat has to be cooled away. And so that's the first job of the cooling tower water, is to cool the absorber, because otherwise it'll just keep generating the heat and it'll get hotter and hotter, and the cycle will grind to a halt. So we got to have a good flow of this 85-degree condenser water. Let's see. And then from here, so it's 85 from the tower, 95 going to the condenser, and about 103 going back to the tower. So we've picked up, what is that, about 8 degrees in the condenser. We picked up 10 degrees in the absorber. So we got about an 18-degree delta T on our cooling tower water. Condenser refrigerant temperature is about 113 degrees, which is the saturation temperature at about 70 millimeters of mercury, which was what, 1.35 psi. So that's what's going on up here. Okay, next, refrigerant passes through the orifice to the evaporator. This is, we're showing just one orifice. There's several in here, really. But these are sized so that we keep some depth of water built up on top of this, in order, it kind of seals the high pressure side from the low pressure side. And this pressure forces the water flow through this orifice. So we have low pressure down here, and then we get some, that's the expansion. It's kind of the expansion valve for these orifices where we drop pressure, we vaporize a little bit of the water, and that cools the rest of it. And then it flows, the liquid flows over the evaporator tubes to keep them soaked with liquid water, so they will, the water will continue to evaporate, provide the cooling effect. And then we've got a little tray down here that catches any water that didn't get vaporized, runs down through a pump, and then we pump it up. So we're constantly spraying this cold liquid water refrigerant on the outside of these evaporator tubes. So this is where the cooling effect occurs in the evaporator. So we have our chilled water coming back from the system, maybe 52, 54, 56 degrees, and then being cooled to 42, 44, something like that, being sent back out to the system. Okay. Condenser pressure, again, is about 70 millimeters of mercury, which is nearly 10 times more than the evaporator, which was what? I think it was, well, it was 0.12 PSI-A. I forget the millimeters of mercury right now. Too many units. What was that? What was it? I guess it's about 7. It's 10 times more than the evaporator. So it's, yeah, it's about a factor of 10. So it's about 7. Okay. Okay. Let's see. So yeah, we'll finish this one. Let's see how we doing here. Okay. I'm just checking the time. Let's see. So as refrigerant passes from the high to the low side, some of it flashes, so that's the effect of going through that pressure drop, and cools the remaining liquid to the temperature corresponding with the evaporator pressure, which is, there you go, 6.2 millimeters of mercury, which is about 40 degrees Fahrenheit. So by controlling that pressure, you control the temperature at which the phase change occurs. Okay. Refrigerant, flash cooled by the pressure drop, falls into a collection pan at the bottom of the evaporator. So it comes out first, it falls on these tubes and it doesn't all get evaporated. So then it falls down to this collection pan. It gets pumped back up, and there's a continual spray, the discharge of this pump up to these little nozzles up here spraying on the evaporator tubes. Okay. So I think that's that one. So some definitions in terms of the lithium bromide solution. Typically 3 concentration levels of solution can be found in the system, and they're defined to be strong solution. So it's strong in terms of the concentration of lithium bromide, which means it has a low water or refrigerant content. So that's in the generator is where we're boiling off that refrigerant. So that's where we drive up the concentration of lithium bromide. Intermediate solution is a mixture of dilute solution and concentrated solution. We'll see that in a second. Let's get sprayed, the absorber spray tree, which sprays out in the absorber to promote the water combining back into solution with the lithium bromide. And that's where that heat is given off. And then dilute solution, that's what gets pumped back up to the generator. That's where we have put all the water that we can get back into the lithium bromide, and that's in the absorber sump. So we can look at it. Dilute solution is formed in the absorber section. So see, that's down here in the bottom. So we do the absorbing. We put the water and the lithium bromide back together in the absorber. Again, it gives off heat. We have to cool away. But then down here at the bottom in this well, we get the dilute solution, which has the most water. So the smallest concentration of lithium bromide, which is about 58%. Okay. Dilute solution has little to no practical absorbent qualities, so it's pumped to the generator to be reconcentrated. So that's about the most water you can get to absorb in there. So then basically we're going to pump it back up. We're going to go through a heat exchanger first, just to change some heat, but then it's going to go up here to the generator where we're going to heat it up, and then we're going to boil some of that water out of here to make the cycle, provide the refrigerant vapor, so the cycle will work. Okay. Strong solution is produced in the generator section and has high absorbent qualities. So we only, the smallest concentration of lithium bromide is 58%. The max is 65%. So it doesn't change as much as you might think. Strong solution. So we produce the strong solution up here by boiling off the vapor. And interestingly enough, R718 is water. So water actually has a refrigerant number assigned to it. So R718 is boiled out of solution, leaving behind a strong lithium bromide solution in the generator, which then gets pumped back down into the cycle so that it can pick up more water vapor and then bring it back. Max allowable strong solution at full load is about 65%. We noted that previously. The intermediate solution is a combination of dilute and concentrated solutions. This is about 62%. So what happens is that this strong solution comes back from the heat exchanger, heading back down, because we want to cool it back down again. And so we're wanting to heat up this stream going to the generator. So it just makes sense to exchange energy to cool this guy down and heat this guy up, requiring less energy input in the generator. But so that strong solution comes down and it's introduced with some weak solution at the suction of the pump that's then pumping up to the absorber spray tree. And so this is the 62% is the result of mixing 65% and 58%, which then gets pumped up here and sprayed out into the absorber to put the refrigerant, the water, back into solution with the lithium bromide. Okay. Okay, the intermediate solution is sprayed throughout the absorber section to absorb refrigerant vaporized in the evaporator. So, you know, we generate vapor up here at high pressure, we condense it, we drop pressure, we spray it on the tubes, it evaporates, then the vapor migrates down here to the absorber where it gets put back together with the lithium bromide and eventually goes back to the generator. This absorption, as this absorption occurs, the low pressure occurs because lithium bromide is absorbing water vapor from the evaporator, so it keeps the pressure low down here because we've got these molecules floating around and then they get combined, so they get taken out of the space, and that tends to want to keep the pressure low. Lithium bromide becomes saturated with water vapor and falls to the absorber sump, where it's now dilute solution and is held for recirculation. You know, so then this pump would pump it back through the heat exchanger to preheat it, and then back to the generator to have the vapor boiled off again. Performance operation. After the intermediate solution has absorbed water vapor and had its heat transferred to the tower water, because remember that's exothermic, so that's going to give off some heat. It becomes dilute 58% and cooled to about 103, and so that's the temperature at that base of the sump at steady state full load. Dilute solution is stored in the absorber sump where it is recycled to the generator. Okay, the diluted solution can no longer absorb, so a pump is used to move it to the generator. It's kind of a little redundant. However, before entering the generator, it must pass through a heat exchanger. Heat exchanger exchanges heat between the strong solution and dilute solutions at an efficiency of approximately 70%. So 70% of the available heat gets transferred from the hot strong solution to the weak solution going back up. Strong hot solution from the generator, about 214 degrees, preheats the cooler weak solution from 103 to about 175. So you see the temperatures were 103 down here. We pull out, when we come out of the heat exchanger, we're about 175. There we're showing this coming out at 214, and it gets dropped to 135. So that's the function of that heat exchanger. And this just shows you kind of a picture of the box. Here, the concentrated hot solution, 214 in, 135 out, and the cool dilute solution, 103 in, 175 out. So helps the efficiency of the cycle. The heating medium continues to heat the solution, causing water to boil, leaving strong solution behind, which is 65% lithium bromide at 214 up here, which is then coming down here. As the strong solution flows by gravity through, they're showing it flowing by gravity, so it's not pumped. This pre-cools the strong solution to mixing with the dilute solution, which is going to mix down here. I think let's get through this pretty good. This is the complete schematic for the absorption cycle. Okay, so you should probably go back and work your way through this. We will, when we get to our first test, which is still several weeks away, we will ask you some, to regurgitate some of this to make sure that you understand how this cycle operates. And there's some more slides here. I think this is enough for today, and I'm going to cut this off, and I will entertain any questions. Does anybody have any questions they'd like to raise at this point? Throw it out to you guys for a minute. Okay, hearing none. If you have questions on the homework or something like that, I know Chandler, if you're out there, you sent me a question. I didn't do a very good job of answering it, but why don't you email me, or you can stay on after we for a few minutes if you want to discuss, and anybody else is welcome to as well. So I'm going to stop the share right now, and like I said, I'll hang around for a few minutes if there's any questions. If not, I'll be in touch. As far as, I don't know, my wife gets her COVID test results back by Monday, by the end of business on Monday, then I should know about Tuesday, but I will be emailing you to let you know if I will be in class on Tuesday. So hope everybody has a great day, stay safe, and be back in touch.
All right. I'm gonna hang around a little bit.
That's a great idea, Chandler. Man, did I ever blow your question? That was pitiful.
Well, I actually went to the class, so I probably would have missed it even if you did answer it. I was late getting to the Zoom.
Well, I'm sorry. My wife woke up this morning and had the fever, and we're sitting there going, I was supposed to go to a plant tomorrow up in East Tennessee, and I had to cancel out of that because everybody's scared to death these days.
What plant were you supposed to go to?
Shot Gemtron. It's up. Where is it going to stay? In Sweetwater. The team's still going. I just can't go with them because I might infect somebody.
Yeah.
Go ahead on your question.
So when I simulated it, I was trying to find the peak demand on it, and all of my outputs on demand were reading 0, but then I still had the demand charge. So I just had to use the charge to get a peak demand.
Well, that's interesting. Let me let me go back to a screen share. Let me pull up this result that I just ran. Let me get out of this. If I can get that. Let's see. Let me just run it again real quick. It's probably quicker. So when you went down to the bottom here, it showed 0 demand. Did you run the electric bill details? So here's your demand right here.
Okay. So I might have been looking. I need to probably just pull mine up to see, but I might have just misread the chart where it has all the zeros. Is might have been what
Yeah.
was throwing me off.
Okay, well here, I'll stop share your screen and throw your model up.
Alrighty, I didn't save my modifications to it, but it should still run the same. Okay, I'll go ahead and share it. Actually, you'll have to, I think, make me host so I can share.
Yeah. Oh, well, I'm sorry.
Oh, that's all good.
I'll make you co-host.
All right.
There you go. We can share the limelight here.
All righty.
Okay.
It should probably be about the same as yours, which I didn't. Yeah, it looks the exact same as yours, but where all these were zeros, I thought maybe the overall was like a sum of it or something. And like this one, the maximum demands, like peak is where I thought it would be. But
Yeah, I mean, I'm not sure. I don't think mine. I think mine had zeros and all those too. But I mean, this is your.
yeah. Well, the 600 is what I actually calculated, but dividing it by the cost,
Okay.
so
Okay.
worked out the same.
Okay. Well, that's fine. Now, when you asked that question, I was deep in the other course, and I'm sitting there going, "What? No, what's he doing?" Because we were kind of doing similar lingo in both classes, and so I blew it. I'm sorry.
Oh, it's all good.
Okay. Well, so are you straight on this?
I reckon so. Yeah, it's just a weird chart they had there.
Well, and I mean, I can't claim complete understanding of. I mean, you could probably look under the help, the F1 under electric bill details, and you could probably figure out if you work at it long enough, you could, I mean, it may be that the rate structure has to be defined in a certain way before it's going to show you peak and off-peak demands.
Yeah.
So if it's not, go ahead.
I was just gonna say that the peak and off-peak demand charge was the same, so might be why it threw it off or something. I don't know.
I don't know. I mean, it's a big complicated program, So
Yeah.
I don't know. Okay.
But, also, I kind of am confused on that evaporator or the absorber. I mean, on its use.
Oh, okay. Well, so you've got to get the lithium bromide, the absorber now, the lithium bromide, the carrier, and the water have to get back together in solution. Okay.
So it's like went through a chiller, and then this is like a post chiller cycle.
No, this is all part of the chiller. This is inside the chiller.
Okay.
It's just like with the mechanical, you've got a compressor, you got an evaporator, condenser, and expansion valve, and that's all inside the chiller. That's what makes it work. Well, so in the absorption, it's just a different type of chiller. I guess I should pull up some pictures. And I mean, they look kind of halfway similar, but you can tell there's something different for sure. And so, it's just a component that's part of the absorption chiller that a standard chiller won't have, because so we pick up the absorber and the generator and some of these little pumps.
Okay. Yeah, I was I don't know, I just felt kind of dumb. Sat here and listened to a 30-minute lecture on it. Don't even know what it does.
Oh, well, I mean, we're not finished, and we can regurgitate and go through again. But basically, it does. I mean, it makes cold water.
Okay.
Which is what the centrifugal chiller does. I mean, they both serve the same purpose. They're just different cycles, and this is something most people don't come out of thermo with. I mean, you just don't have time to talk about it. And so, it's a viable technology that's out there. that, part of the HVAC world that you need to know about.
Yeah. All right. Well, I understand a little better now. I appreciate it.
Sure. Well, if you think about it a little bit, you just punch those slides. There's also some very good notes. Those slides came from Train, and they actually put comments at the bottom of the slide, and their comments are quite good. Each slide they'll have 3, 4, 5 sentences down there discussing the slide and giving additional information. I've read all that stuff a couple of times. I try to remember to make all their comments, but sometimes I don't. But since you have the PowerPoint, you can actually, look at the comments down there, and they're quite good.
Okay. Okay. Yeah, I see it now with the notes button.
Yep.
All right. Well, I appreciate it. I hope your wife doesn't have COVID.
You and me both. You won't see me for a long time if she does.
Yeah.
So I don't know. We'll see. I think, well, you just don't know. She was okay last night and had a fever this morning. So we'll find out. That's the way it works. Does anybody else have any questions there's some other folks still on? Nope. Okay. Well, I guess that's it. I will stop the recording here, and we'll get this thing posted. I appreciate everybody attending. Hope you guys have a great day.
You too. See ya.
See ya.